Hello! In this video, we are going to prove the following theorem. The arctangent function maps onto the open interval negative pi over 2 to pi over 2. Now, let's first remind ourselves of our definition of the arctangent function. Let x be any real number and consider the following sequence. Then, the sequence 2 to the n xn converges. And we define the value that this sequence converges to be the arctangent of x. Right? And from here, we've proven several properties of the arctangent function. One of which is that the arctangent function is a strictly increasing function. And also, the arctangent function is continuous. We also proved that the arctangent function is bounded. From there, that told us that the arctangent function has a least upper bound and a greatest lower bound. And we defined pi over 2 to be the least upper bound of the arctangent function. And from there, it followed, using the fact that arctangent is an odd function, that negative pi over 2 is the greatest lower bound of the arctangent function. And from there, we proved two limits. We proved limit as x approaches infinity of arctangent of x is equal to pi over 2, and limit as x approaches negative infinity of arctangent of x is equal to negative pi over 2. Now, by definition, this limit means the following. It means for every epsilon greater than 0, there exists a real number capital N, such that for all x greater than or equal to capital N, the absolute value of arctangent of x minus pi over 2 is less than epsilon. And also, by definition, this limit means the following. It means for every epsilon greater than 0, there exists a real number capital N, such that for all x less than or equal to capital N, the absolute value of arctangent of x minus negative pi over 2 is less than epsilon. Okay, so now let's get into proving this theorem. Now, to prove this, what we're really trying to prove here is for every real number w in the open interval negative pi over 2 to pi over 2, there exists a real number c such that the arctangent of c is equal to w. So to prove that, let's first give ourselves an arbitrary real number w in the open interval negative pi over 2 to pi over 2. And then, since we know that this limit is true, this means we know that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number pi over 2 minus w. Right? We know pi over 2 minus w is positive because, well, we know w is less than pi over 2. So if we subtract w to the other side, we have pi over 2 minus w is positive. So we can take epsilon to be pi over 2 minus w. And with that choice, we have that there exists a real number I'll call b, such that for all x greater than or equal to b, the absolute value of arctangent of x minus pi over 2 is less than pi over 2 minus w. So this statement works for all real numbers greater than or equal to b. So in particular, it must work for b. So taking x to be b, we have that absolute value of arctangent of b minus pi over 2 is less than pi over 2 minus w. And remember, every output value of the arctangent function is in the open interval negative pi over 2 to pi over 2. So every output value of the arctangent function is less than pi over 2. So in particular, the arctangent of b is less than pi over 2. So the absolute value of this should be equal to pi over 2 minus arctangent of b. So we have that pi over 2 minus w is greater than pi over 2 minus arctangent of b, and that implies w is less than the arctangent of b. And next, since this limit is true, this means we are given that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number w plus pi over 2. Right? We know that w is bigger than negative pi over 2. So if we add pi over 2 to the other side, we get w plus pi over 2 is greater than 0. So we can take epsilon to be w plus pi over 2. And if we do that, well then, there exists a real number I'll call a, such that for all x less than or equal to a, the absolute value of arctangent of x minus negative pi over 2 is less than w plus pi over 2. And this statement works for all real numbers less than or equal to a. So in particular, must work for a. So taking x to be a, we have that the absolute value of arctangent of a minus negative pi over 2 is less than w plus pi over 2. Next, let's just join these two guys into a plus pi over 2. And then the arctangent of a plus pi over 2 is positive because we know every output value of the arctangent function is bigger than negative pi over 2. So in particular, arctangent of a is bigger than negative pi over 2. So if we add negative pi over 2 to the other side, we get arctangent of a plus pi over 2 is bigger than 0. So we can get rid of the absolute values here. And now we see w plus pi over 2 is bigger than arctangent of a plus pi over 2, which implies that arctangent of a is less than w. And let me just remind you, w is less than arctangent of b. So now, we have introduced two real numbers, a and b. And there's three possible ways that a and b can be related. Either a is less than b, a equals b, or a is greater than b. But since arctangent is a strictly increasing function, the only possibility is that a is less than b. Because if we instead have a equals b, then arctangent of a equals arctangent of b, which is false. And if a is greater than b, then strictly increasing implies arctangent of a is greater than arctangent of b, which is false. So the only possibility is that a is less than b. Now remember, the whole goal has been to find a real number c such that the arctangent of c is equal to w. To see how we could find that real number c, let's visualize the graph of arctangent between a and b. Since arctangent is a strictly increasing function, maybe the graph looks something like this. So this is the arctangent of a, and this is the arctangent of b. And w is some real number between arctangent of a and arctangent of b. Maybe w is right here. And notice in our diagram, we see that there is a real number c, such that the arctangent of c is equal to w. And it seems that the continuity of arctangent is what is making this situation happen. In fact, what's really going on here is the intermediate value theorem. If we recall, the intermediate value theorem tells us the following. Suppose I is an interval, and f is a function whose domain is that interval, and f is continuous on I. Also suppose that a and b are elements of I such that a is less than b. And suppose w is a real number such that f of a is less than w is less than f of b. Then there exists a real number c in the open interval a comma b such that f of c is equal to w. So, applying the intermediate value theorem to our proof, we're really working with the arctangent function. So we're going to take I to be the set of real numbers, we'll take f to be the arctangent function, and we're going to take a and b to be the a and b that we have in our proof. We'll take w to be the real number w that we have in our proof. Well, in this case, we know that the arctangent of a is less than w is less than arctangent of b. That's precisely what we have here. So, by the intermediate value theorem, we can conclude that there exists a real number c in the open interval a comma b, such that the arctangent of c is equal to w. Putting this all together now, we see given any real number w in the open interval negative pi over 2, comma pi over 2, there exists a real number c such that arctangent of c is equal to w. And that proves that arctangent is onto. And so this completes the proof. Now, this is really similar to the proof that we gave, proving that the real exponential function maps onto the positive real numbers. In fact, in this proof and the proof with the real exponential function, there really isn't anything special about those functions, right? You can generalize this to any function which has properties like these. So now, let's talk about what we know so far about the arctangent function. We know that the arctangent function is a function from the real numbers to the open interval negative pi over 2, pi over 2. Right? In other words, for every real number x, the arctangent of x belongs to this interval. And we know that the arctangent function is a strictly increasing function. And that tells us that the function is 1-to-1. Right? 1-to-1 in the sense that distinct input values map to distinct output values. And we also just proved that the arctangent function is onto. And so this information tells us that arctangent has an inverse function. And so we define tangent to be the inverse of arctangent. Right, and so the inverse is going to be a function from the open interval, negative pi over 2 to pi over 2, to the real numbers. And by properties of inverse functions, we have the following. Right, we get these two facts. Also, since arctangent is a strictly increasing function, we have that tangent is a strictly increasing function. Since arctangent is continuous, it follows from properties of continuity that tangent is continuous. Now, when we say continuous, it's continuous on the open interval negative pi over 2 to pi over 2, right? Continuous on its entire domain. Now, soon, we will extend the definition of tangent to a larger domain, right? We'll define the trig functions sine and cosine, and we'll show for all x in the open interval negative pi over 2 to pi over 2, the tangent of x is equal to sine x over cosine x. And then we'll use that to extend the definition of tangent to be sine over cosine for larger domain. Right, so this is pretty much where we're at so far. So yeah, that's pretty much it for this video.